Okay, so we are looking at page 39, and we're going to continue on with some example math problems on page 39. So we're going to start with an example of Boyle's law, and with these calculation problems, we're going to be using our old friends, the guess boxes. Let's remind ourselves real quickly what each guess box is. The G stands for given, where you're just going to list every number that they give you in the problem, and the variable that goes with that number. U is for unknown. What are they asking you to find? The E is for the equation that you're going to use to solve your problem. The first S is where we substitute. So instead of using the equation with the variables, the letters, you're going to plug in numbers instead. And the final S is where you write the solution, your answer. So, as we're doing a given, let's look at this problem. It says it's a Boyle's law problem. At a pressure of 405 kilopascals, the volume of a gas is 6.00 liters. Assuming the temperature remains constant, if the new volume is 4.00 liters, what will the pressure be? So we've got several things here. They tell us this is a pressure of 405 kilopascals, so that given 405 kilopascals, that is a pressure. They tell us that they have a volume that is 6 liters, so I'm going to put 6.00 liters, and our variable for volume is a V. Then they say the new volume is 4.00 liters. So 4.00 liters is also a given, and they tell me that that one's a volume too, so I'm going to label that with a V. And they ask, what will the pressure be? So they're asking about the pressure. That means pressure P is going to be my unknown. And I need units for my unknown. And I'm going to tell you right now, they should match the other one. So like, this is a pressure, this is also a pressure, that pressure was in kilopascals, so my unknown pressure should match and also be kilopascals. You just have to pick the one that matches. Okay, and if you know your unknown units, you also know the units for your solution, so you can write that down there right now before you forget. Because yes, that is something we grade for, is if you labeled units in your answer. Having that much done, we need an equation. I'll notice that I have 2 P's and 2 V's here, so if we go back to page 38 and look at our formulas, I need one with 2 P's and 2 V's. This one has 2 P's and 2 T's. That doesn't help me. This one has 2 V's and 2 T's. That doesn't help me, but this one has 2 P's and 2 V's. So that is the equation I'm going to need. And notice that is Boyle's law. It says right there. So we're going to copy this equation down into the E box in our guess boxes. So P1 V1 equals P2 V2. And again, they didn't write it in there, but when you have 2 variables written next to each other like that, you're supposed to multiply them. They're being multiplied. Now we have a little bit of a problem, which the formula has these 1's and 2's, and our given and unknown currently do not have any 1's or 2's. Those 1's and 2's just mean first and second. So let's go back into the problem. You'll notice that in the problem where they told us 4 liters, they said 4 liters was the new volume. I'm going to tell you right now, if they ever say the new something, new is code for 2. So 4 liters is the new volume, that's V2. And that means that 6 liters must be V1. If we think about the pressures, they're asking what will the pressure be, like later, like second. So they're asking for the new pressure. And that means the pressure they gave me at the beginning, that was my first pressure. So once you have everything labeled with including the 1's and 2's, then we're ready to substitute. So we're just going to say, okay, well, P1 was 405. So instead of writing the letters P1 here, I'm going to write 405. That's times V1, which was 6. So times 6.00 equals P2 we don't know. So we can either rewrite that variable P2 here. You could also just, instead of writing P2, you could put like X if you want. That's fine. Okay, same thing. And then that's going to be times V2, which was 4. Okay. There are a couple different ways you could correctly solve this algebra. Either way, I'm going to go ahead and say you should probably combine these terms here and do the multiplication. 405 times 6. That is 2430. And that equals x times 4.00. That's the same thing as 4.00x. Yeah. And then to solve for x, remember that you have to, these are being multiplied. And if you want to get x by itself, you want to isolate x, isolate the variable. You got to get rid of this 4.00 by doing the opposite of what's happening to x right now. Right now, x is being multiplied. You have to do the opposite of multiplication, which is division. So we got to divide by 4.00 on this side to get x by itself. And if you do it on one side, you got to do it on both sides. So we're going to do 2430 divided by 4.00. And you get 607.5 kilopascals. Okay, let's move on to page 40. Charles's law. It says at 242 Kelvin, a sample of oxygen gas has a volume of 325 milliliters. If pressure is held constant and the temperature is lowered to 189 Kelvin, what would the new volume of gas be? So again, we're going to just do the easy parts first. Start by just writing your givens out. We have 242 Kelvin. We have 325 milliliters. And we have 189 Kelvin. And we need to label these numbers with variables as well. Kelvin, if you recall, Kelvin is our unit that we're going to use in gas laws for temperature. Okay, Kelvin goes with T. Capital T is our variable for temperature. So both of these that say Kelvin are temperatures. And then they say 325 milliliters is a volume. They use the word volume there, so I can label this V for volume. Notice they're asking me what would be the new volume. We said earlier new is code for 2. So they're asking me not just for a volume, but for V2. Which means that this other volume here, if they're asking for V2, this volume must be V1. And if V1 was milliliters, I'm going to need V2 to also be milliliters. When you start talking about the temperatures, it says it's at 242 and then it is lowered to 189. So it starts at 242 and then it is lowered. So 189 is what is the second temperature. 242 is what we started at before it was lowered. So 189 is T2, 242 is T1. From here, we need an equation. I have V1 and V2, T1 and T2. If I look at my equations, there is an equation that uses V1 and V2 and T1 and T2. It's called Charles's law, which conveniently is what this problem was labeled as well. So V1 over T1 equals V2 over T2. And again, now we go substitute. We're just going to plug numbers in. V1 is 325. So instead of writing the letters V1, I'm going to write 325. Over, that means divided by T1. T1 was 242, so I'm going to write 242. That equals V2, which we don't know. Again, you could write V2. You can also write just an X if that makes you more comfortable. It doesn't change anything about your answer. So V2 or X if you prefer. Divided by T2. T2 was 189. So I'm going to put 189 on the bottom here. There are a couple of different ways, again, that you could do this algebra and still end up at the correct answer. If you know how to cross multiply, or some math teachers call it the butterfly method, you are more than welcome to do that. I prefer to just simplify what I have here. So I put this in the calculator, 325 over 242. That'll give me 1.34 equals V2 over 189. And again, if I'm going to isolate V2, then I need to do the opposite of what's happening to V2 right now. Right now, V2 is being divided by 189. Instead, I need to do the opposite of that and multiply by 189. If I do that on one side, I need to do it on the other side. So I'm getting 253.82 for my final answer. And my answer is missing something. I didn't take the time earlier to remind myself whatever I know for the unknown is milliliters. I know those units have to be the answer to the units for my answer. So I almost forgot to put it. That would have been points off. Sad. Okay, let's talk about the third one. Gay-Lussac's law. At 30 degrees Celsius, a sample of oxygen gas has a pressure of 325 kilopascals. If volume is held constant and the temperature is lowered to -5 degrees Celsius, what would be the new pressure of gas? So we have some givens here again. We have 30 degrees Celsius. We have a pressure of 325 kilopascals, so 325 kPa, and they even tell me that's a pressure, so I can put P for pressure here. Then I also have -5 degrees Celsius, and they tell me this time, they tell me -5 degrees Celsius, they tell me that's a temperature. So that means degrees Celsius does measure temperature. They ask what would be the new pressure of the gas, so they're asking for pressure, and they specifically want the new pressure, so they want P2. Which means that this other pressure is P1. And if P1 is kPa, P2 should also be kPa. And if my unknown is kPa, that means my answer should also be kPa. I also should notice that -5 degrees is when the temperature was lowered, so that happened to it second, so that's going to tell me that's T2, and the other temperature is T1. And I can go ahead if I want and find the formula that I need here. I have P1 and P2 and T1 and T2, and go figure that it will all be matched by Gay-Lussac's law that has 2 P's and 2 T's. So that's going to be my formula. However, we have a problem before we plug this in. And the problem that we have is that your temperature for this whole unit that we're doing right now, your temperature has to be in Kelvin. It cannot be in degrees Celsius. It has to be in Kelvin. So we have a problem because in this Gay-Lussac's law example, this temperature is not in Kelvin. It's in degrees Celsius. So we need to change it to Kelvin first. Kelvin is when you do 2 degrees Celsius plus 273. So we're going to have to, for both of these, do plus 273 and plus 273 to figure out that this is 303 Kelvin. And it is 268 Kelvin. We're not supposed to use Celsius. You can even, like, once you know the Kelvin, you can scratch the Celsius out so you don't accidentally use it. We need Kelvin. We can never use Celsius anymore for this whole gas laws unit. Okay, once we have our kelvins, then we can plug into the formula. P1 is 325. So instead of writing 3.1, I'm going to, instead of writing P1, I'm going to write 325. P1 is divided by, so I'm going to put a division sign, T1, which in Kelvin was 303. So instead of writing the letter T1, I'm going to write 303. That equals P2, we don't know. So you can write the letter P2. You could also put an X if that makes you more comfortable. You could put an X there. Same thing. And that's divided by T2. Instead of writing the letter T2, I can come up here and notice my T2 is 268, so I'm going to put 268 on the bottom here. From here to solve for x, again, if you know the butterfly method, if you know how to cross multiply, be my guest. You can go ahead and do that. What I do is I like to simplify first, 325 over 303. I put this in my calculator, 325 divided by 303, and I get 1.0726, blah, blah, blah. That equals x over 268. And if I want to solve for x and isolate x, I have to move this 268 over by doing the opposite of what's happening now. So right now, x is divided by 268. I have to do the opposite if I want to isolate x. So instead of dividing by 268, I multiply by 268. And when I have done that on one side, I have to do it on the other side. So I end up doing 268 times 1.0726, blah, 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 blah. And when you multiply those, you get 287.46. Our final answer should always still be rounded to the hundredths place. And again, that is kilopascals. There are quite a few problems for you to practice on page 41 with guess boxes on page 42. I, right now, am going to go ahead and label my guess boxes like this is where I'm writing my answer to number 1. This is where I'm writing my answer to number 2. Here's my answer to number 3. Here's my answer to number 4. Because to get your stamp, you definitely have to have all of your work showing. So, and I'll even... Here's on the next page, number 5, number 6, number 7, number 8. There you go.